Hello, everyone, and welcome to Chapter 7. As we begin Chapter 7, we're going to be starting the inferential statistics part of this course. If you remember from early on in the course, I told you that inferential statistics is when you study a sample, and then based on what you learn about the sample, you try to make some conclusion about the population. Well, in Chapter 7, as we start to learn about inferential statistics, we're going to learn something about a confidence interval. Now, a confidence interval is a way for us to estimate a population's mean. You see, if we wanted to know the population's mean, the exact value of it, we would have to study each and every person in the population. And populations are usually pretty big, and it's just not practical to study each and every person in the population. So what we often do is we take a sample out of the population, a small group, and we study that sample. And then based on what we learn about the sample, we can try to estimate the population's mean. And the way we do that is we take our sample average, which you might remember is represented by this symbol X bar, and then we do plus or minus a number that's called E, and that stands for the margin of error. So basically what we do is we say that the population mean should be fairly close to the sample mean that we've got from our study. And so what we'll do is we'll take that sample mean and we'll create a little interval here by doing plus or minus this number E. Now this number E can be found by taking a special z-score. Okay, this subscript here, which is Greek letter alpha over 2, just designates this as a critical z-score. So we've got this z-score times the population standard deviation divided by the square root of the sample size. It's really the central limit theorem that gives us this particular formula for the margin of error. We don't need to get into all the details about where exactly it comes from. We just need to know that this z-score here is going to be related to something called our confidence level. Okay, our confidence level. Our confidence level is going to be the probability that the interval that we come up with actually contains the population mean. There might be a 95% chance or a 99% chance that our interval will contain the population mean. Well, that probability is what we call our confidence level. And based on whatever amount of confidence we want to have in our interval, that will determine what z-score we use in this formula. And I'll show you how we can get the z-score that corresponds to the confidence level that we want to work with. Okay? We can never have 100% confidence when you do inferential statistics because you're not studying everybody in the population. There's no way you can be 100% certain about your estimates. So there's always going to be a chance that your estimate is good, a chance that your estimate is not good. Okay, the chance that you end up with a good estimate, that's our confidence level. Now, if you want to get that z-score that corresponds to your confidence level, what you can do is you can draw yourself a standard normal distribution. You can shade an area in the middle of it and just label the amount of area that you've shaded as whatever percentage you want to work with for your confidence level. Maybe it's 95% or 90% or 99%. Okay, whatever probability you want to have of having a good interval estimate that really captures the population mean, just label that in the center of the distribution where you've shaded some area here. Okay, because of the symmetry that's in this distribution, you can call the boundaries of that shaded region negative z and positive z. Same z-score, just one negative, one positive. So for example, if we wanted to find the z-score for a 95% confidence interval, we could shade the area in the curve here and in the middle and label it 95%. That means 5% of the area is not shaded. Well, that unshaded area is split into two equal parts, half in the left tail, half in the right tail. Half of 5% would be 2.5%. So that's why I've got each unshaded area as 2.5%. The z-score that we need for our confidence interval formula is the one that's on the right side here, the positive one. To get that z-score, what we would have to do is we would have to get the total amount of area to its left and then go to our standard normal chart and try to find that number and get that z-score. Well, we've got 95% area shaded here, plus 2.5 unshaded, that's to the left of the z-score. So altogether, that's 97.5% of the area under the curve to the left of our z-score. In decimal form, that's 0.9750. And if we go to our standard normal chart here, let's see, 0.9750 is in the chart. It's in the row 1.9 and it's in the column for 6. So 1.96 would be our z-score. Now, if you're making confidence intervals for 90% confidence, you can go through that same process that I just showed you, and you would get 1.65 for your z-score. As I just showed you, 95% gives you 1.96. 99% would give you a z-score of 2.58. I would suggest you memorize the 3 z-scores that correspond to these 3 confidence levels, because these are the most common confidence levels that people work with. You may run into a different confidence level at some point. If you do, that's fine. Just go through the process I showed you, draw the standard normal curve, shade in the middle, get the area to the left of your z-score, and then go look it up in the chart. Okay, but these 3 show up the most, so I would suggest that you memorize these 3 z-scores. Okay, so let's see if we can actually create a confidence interval now that we know a little bit about what the formula is and how to work with it. So here we have a sample of 40 people that was selected, and they were asked to walk 1 mile. The average time that it took them was 15.7 minutes. The population standard deviation is known to be 2.3 minutes. If we want to compute a 95% confidence interval for the population's average time to walk 1 mile, here's what we would do. We would take our sample average plus or minus this number that we're calling the margin of error, represented by E. And we know that E is equal to the z-score times the population standard deviation divided by the square root of the sample size. So for a 95% confidence interval, your z-score would be 1.96. And then we said the standard deviation was 2.3. And we divide that by the square root of 40, since 40 was the sample size. You can multiply that out on your calculator, 1.96 times 2.3 divided by the square root of 40, and you should get 0.7. I'm rounding that to 1 decimal place because the sample average I have has 1 decimal place. And since I'm going to add and subtract this number with the sample average, it makes sense that we match them up in terms of decimal places. So take 15.7 plus or minus the 0.7. Do the minus first, so you get the low end of your interval estimate first. That would be 15.7 minus 0.7, which is 15.0. And then the upper end you would add, so 15.7 plus 0.7 would give you 16.4. You can say there's a 95% chance that the population mean is somewhere between 15.0 minutes and 16.4 minutes. Obviously, that means there's a 5% chance that it is not. Okay, so the whole idea here behind confidence intervals, it goes back to the central limit theorem. Not only do these formulas kind of come out of the central limit theorem, but the principle behind these intervals really comes out of the central limit theorem as well. Remember, I told you in the central limit theorem video that one of the principles that comes out of the central limit theorem is that the sample mean and the population mean tend to be close together most of the time. So when we take our sample mean here and do plus or minus with some number, basically we're saying that, well, most of the time this is going to capture the population mean, because most of the time our sample mean will be close to the population mean. If we just give ourselves a little bit of wiggle room on each side, then most likely our interval will capture the population mean. Okay, it won't always do that, but most of the time it will. In this case, 95% of the time it will. Now let's say we wanted to do a 99% confidence interval, so we wanted to be a little bit more confident. Well, the only change that we would have to make is we would use 2.58 for the z-score. Everything else stays the same. So take 2.58 times 2.3 divided by the square root of 40, and you get 0.9. Then take your 15.7, the sample average, plus or minus 0.9. Doing the minus first, 15.7 minus 0.9 gives you 14.8. Then add, and you would get 15.7 plus 0.9, and that's 16.6. So what I want you to notice is that in order to have more confidence in your interval, you need to have a bigger interval. Okay, a bigger interval will give you more confidence. Or flip that statement around, if you want more confidence, you're going to need a bigger interval. Okay, now there's a trade-off here that we sometimes have to balance. Of course, we would want to be more confident in our interval estimates. Okay, we would like there to be a really good chance that the interval estimate is accurate and really does contain the population mean. The problem is, if we want to be more and more confident, our intervals are going to get bigger and bigger. Well, if we let our intervals get too big, then the size of the interval might not allow us to get any meaningful information from it. Okay, for example, if I told you that the average age of all the people who live in the state of Maryland is somewhere between the age of 2 and 82, you'd probably say, you know, big deal. Why'd you tell me that? I could have told you that. Okay, so if you have a big interval, it might not give you very meaningful information. So sometimes you have a trade-off here that you want to balance. You want to have a lot of confidence in your interval, but at the same time, you don't want it to get too big where you lose the meaning and the precision from it. Okay, well, in these situations, when we're trying to balance the trade-off, the way we do that is we have to choose our sample size appropriately. So if you want a certain confidence level and you want to limit the size of your interval so that it doesn't get too big, then you're going to have to choose your sample size appropriately. Here's how we know that. Look at our margin of error formula. Now, if we want a certain confidence level, that means the z-score is fixed. Population standard deviation is what it is. We have no control over that. Now, if we also want to put a limit on how big the interval gets, that means we're going to need to put a limit on E. Well, if those three numbers are already determined, the only one that we have any freedom to do anything with is the sample size. So here's what I've done. I've taken this formula and I've done the algebra to solve it for n. And when I rearrange everything so that it's solved for n, the formula looks like this. It's a z-score times the standard deviation divided by the limit that we're putting on the margin of error, and that whole expression is squared. And this is another one of those special formulas where no matter what result we get, okay, if it's a decimal result, we have to round it up to the next highest number. Okay, and the reason why is because see how the sample size is in the denominator of the margin of error formula? If we round the sample size up and make it a bigger number, that means the margin of error will go down and it will stay within our limit. If, however, we were to round the sample size down, we would be dividing by a smaller number and the margin of error would go up and it would exceed our limit, which we don't want to happen. So if we get a whole number out of the formula, fine, you can keep it, but that rarely happens. Usually you get a decimal, no matter what the decimal is, you have to round it up. Okay, let me show you an example so you can see how that works. Here it says a large company wants to estimate the average number of sick days used by all employees in a year. They want to limit the margin of error to be within 0.5 days. So in other words, when they make their estimate, they don't want to do plus or minus with any number that is bigger than 0.5. They also want to be 95% confident in their estimate. They know the population standard deviation is 2.5 days. What's the minimum sample size that they should use? Okay, well, we'll take our sample size formula here. Since they want to be 95% confident, we'll put 1.96 in for the z-score, times the standard deviation of 2.5, divide that by 0.5, and then square the whole thing. So if you take 1.96 times 2.5 divided by 0.5, now let me see what number you would get there since I don't have it written. Looks like you would get 9.8. If you take the 9.8 and you square it, you get 96.04. Now, sample sizes always have to be whole numbers. You can't have 0.04 of a person in your study. It's either got to be 96 or 97. And as I explained to you just a minute ago, when you get a decimal result out of this sample size formula, you have to round it up to the next highest whole number. So even though 96.04 would normally round down to 96, you got to go up to 97 in this case. If we go up to 97, then what will happen is the margin of error will go down. And when we make our confidence interval, we might be doing plus or minus with a number like 0.49, which is a little bit less than 0.5. And so that's fine because it's within our limit. But if we were to round our result down to 96, that means the margin of error will go up a little bit, and it might be something like 0.51, which is a little bit bigger than our limit. So sample size formula is another one of those special formulas where you always have to round up. Now, at this point, what you would do if this were a real life study is after figuring out what your sample size needs to be, then you would go select your sample and get your sample average, calculate your margin of error, and then create your confidence interval. So it's almost like this would be the preliminary work if you were trying to balance that trade-off. Sometimes you don't care about the size of the interval. You just want an interval that has a certain confidence level. If that's the case, fine. Just pick any sample size that's 30 or more so that the central limit theorem applies, and then just go ahead, create your interval, and let it be whatever it is. But if you do care about how big your interval is, in addition to the confidence level, then you'll want to choose your sample size first, then select your sample, get the sample average, and go on and create your confidence interval. Okay, now there's another question that we have to consider here in Chapter 7. What if we don't know the population standard deviation? In real life research, you almost never know the population standard deviation. And our formula for the confidence interval assumed that we did know this value. You see, you probably won't know the population standard deviation because in order to get the population standard deviation, you would have to know the population mean. And we talked about how it's just not practical to get the population mean. Well, if you had the population standard deviation, and that means that you had the population mean, why would you even be trying to estimate it? If you have the exact value, it's pointless to estimate it. Okay, so in real life research, we're almost never going to know the population standard deviation. So what do? Well, if we need to create a confidence interval and we don't know the population standard deviation, what we do is we use the sample standard deviation instead. Okay, so remember S represents sample standard deviation. Now, if we use the sample standard deviation instead, we have to make one slight adjustment to our confidence interval formula. We have to use a t-score instead of a z-score in the margin of error formula. So notice in this case, the confidence interval is still the sample mean plus or minus the margin of error, but now the margin of error is a critical t-score times the sample standard deviation S over the square root of the sample size. So if you put the sample standard deviation in place of the population standard deviation, that's fine, but you have to get a critical t-score rather than a critical z-score. And we'll do an example here in just a minute, and I'll show you how to get that t-score. Okay, so here's an example. A sample of 8 elephants had an average weight of 12,300 pounds. The sample standard deviation is 22 pounds. Okay, that's the more likely scenario in real life research. You study your sample and you get your sample mean and your sample standard deviation, and those are the values that you have to work with. Okay, what if we want to find a 95% confidence interval for the population mean? Now it says we can assume that the variable is normally distributed. Since our sample size is less than 30, we're going to have to do that. Okay. Anytime we work with confidence intervals, anytime we're doing anything where central limit theorem comes into play, if the sample size is less than 30, we need to know that the variable, the population, is normally distributed. That's true whether we're working with z-scores or with t-scores. Okay, so in this case, the sample size is only 8, so we needed to know that the population was normally distributed. If it wasn't, the z-scores or the t-scores wouldn't work the way they're supposed to work. Okay, well, since I have sample standard deviation here, notice that when I create the confidence interval, I'm using the version of the formula that has the t-score in it with the sample standard deviation. Now, how do we get this t-score? Well, in the formula card, just below the standard normal chart, there's another chart. It's called the t-distribution chart. And in this chart, which we're going to use in the next chapter as well, when we learn about something called hypothesis testing, you can get critical t-scores. Okay, so how does this work? Okay, well, first of all, we're doing confidence intervals. So you kind of want to focus on that top row here. And I believe I said we're going to do a 95% confidence interval here. Yes, so 95% confidence interval. So our confidence level is 95%. So what that means is we want to go to the middle column here where the confidence level is 95%. Don't worry about these rows that say one tail or two tail. That's for the next chapter. Okay, just focus on that top row, confidence intervals, 95% confidence level. So you're going to work here with the middle column. Now, notice all these rows are labeled DF. That stands for degrees of freedom. You don't really have to worry too much about what degrees of freedom means. You just need to know that when you're making a confidence interval, degrees of freedom is equal to the sample size minus 1. Okay, sample size minus 1. So in our case, where the sample size is 8, the degrees of freedom would be 7. 8 minus 1 is 7. So you just take the t-value that's in that location of the chart, so it looks like it's going to be 2.365, and you use that as your critical t-score. Okay, so I take that 2.365 times the sample standard deviation 22 over the square root of the sample size 8. Multiply it out, that gives you 18. So you can take your sample mean, which was 12,300, plus or minus the 18. Do the minus first, you get 12,282. Then do the plus, you get 12,318. So you can say there's a 95% chance that the population mean is somewhere between these two values. Okay, so when you're asked to make a confidence interval, just look to see, are you given the population standard deviation or the sample standard deviation? Population standard deviation, use a z-score. Sample standard deviation, use a t-score. Okay, so this is inferential statistics. We're going to learn more inferential statistics in the next chapter. I'll see you in those videos.